Hello everyone. In the last module, we looked at heat transfer conduction resistances in series and parallel. So, if we just revisit that a minute. So, for a plane wall, we said R conduction is going to be L over Ka and convection is going to be 1 over Ha. And we also said that when we have multiple resistances in series, that is obstructions to the heat transfer in series, we are just going to add them. So, this is between say T1 and T2, these are two intermediate temperatures Ts1 and Ts2. This could be R1, R2 and R3. We will say R total or sigma R is nothing but R1 plus R2 plus R3, and therefore, Q is equal to T1 minus T2 divided by summation of R total. This was the general equation that we had. So, the summation R total would change depending on when the resistance were in series or parallel. So, when the resistances are in parallel, when will that be? We said if there are multiple paths for heat transfer across the same temperature difference. That what do I mean by that? So, if I have a wall which is at a temperature Th and the surrounding fluid is at temperature T infinity, there is convection to that. So, we have 1 over Ha, there is radiation to that. This is between the surfaces which is at T infinity and the solid wall and the walls which are at T infinity, for example. So, large room, you have a heated plate which is at Th and the room air and the surfaces are also at one temperature, say T infinity. For lack of a better terminology, we will say the radiation heat transfer is given by HR 1 over HR into A, and we looked at that this HR is a pseudo quantity. We said Q radiation is nothing but sigma epsilon A into Th to the power 4 minus T infinity to the power 4. This is between surfaces, and we will recast this in a form that we like. So, Th to the squared plus T infinity squared, A squared minus B squared, and A plus B into A minus B, this one. This will be Th minus T infinity, and we will group all these terms together and we will call it HR into A into Th minus T infinity, which will essentially put this in the form like our convective heat transfer, where H radiation is not a constant. Unlike convective heat transfer coefficient for a given problem, it is not a constant, it is a combination of the temperature of the hot surface and the surrounding surface. So, if the surrounding temperature is constant, that is fine, T infinity could be constant, but Th could be changing with respect to time, and that would be also a function of time. So, H radiation is not a constant. So, it is a mathematical convenience, and that is what we need to understand. We just need to look at it from a mathematical convenience point of view. So, if I have the point to note is, if I have multiple paths for heat transfer across the same temperature difference, so the heat will flow through convection as well as through radiation. Another example would be, if I have a slab, this is slab 1, this is slab 3, in between there are two slabs of two different material, 2A and 2B, both occupying the same space between slab 1 and 2, let us say it is this way in 3 dimension, and let us say this area is A by 2 and this area is A by 2. The surface area for heat transfer is A by 2. This is temperature on this wall and this wall. For example, whatever it may be, the temperature at these two walls will have to be the same, otherwise we will have heat transfer in this way, which we are not having. We are saying heat transfer is primarily in the single direction this way. Okay. So, Q from 1 is going to go to 3, in between it is going to go as Q 1 to 2A to 3 and then 1 to 2B to 3. Okay. So, this is possible because these two surfaces are at the same temperature. So, this is this Ts1 on this side, this is also Ts1, this is Ts2 here, this side is also Ts2. By that they are saying there is a resistance for conduction in wall 1, medium 1, L1 over K1A, and then here it comes we have two paths for heat transfer. So, this is going to be L2 over K2A into A. Okay. Area is nothing but A by 2. This maybe I will change the nomenclature a little bit. P and Q maybe I will put, because A is a little confusing. So, Kp and Kq, Kp A by 2 L2 divided by Kq into A by 2, and these come together at point 3 and you have L3 by K3A. So, these when I want to find the equivalent resistance for this, it is just going to be R1 plus R equivalent of 2 plus R3. R1 plus R equivalent of 2, this is R1, this is R2, I mean R3, and what you will see here is R equivalent is these two in parallel. So, parallel of this would be 1 over R equivalent 2 is 1 over L2 by Kp A by 2 plus 1 over L2 by Kq A by 2. I will put it in the next slide. Let us just go back here, all this is written here already. So, that is what is shown in this set of slides. So, you have a path from E to F and to H, from E to G on to H, and that is what is shown here. So, you have an equivalent resistance which is what is between LF by KF by A by 2, LG by KG A by 2, and you get the equivalent thermal circuit diagram this way. Okay. We also spoke about thermal contact resistance, and we said it is a function of the interstitial spaces, etc. So, air is going to be a bad conductor of heat. So, once you have an air gap, there will be a temperature drop, and that is not a good thing for heat transfer. So, you can apply some pressure, you can use thermal contact grease, which will be able to reduce the temperature drop, reduce the contact resistance. How do you take it? Contact resistance is essentially a number that will be given to you, and you will just use it as this form, that is RTC double prime per unit area is essentially that temperature difference divided by the heat flux, because heat is going to be constant. So, the problem will adjust itself to account for the contact resistance. It is not that you are trying to put in some Q and something is lost in the middle, it is not like that. The net heat transfer that the problem will allow is taking into account the contact resistance. So, Q double prime would be something which you will calculate keeping contact resistance in mind. That is something you need to remember. Thermal conductivities exceed that of the interfacial fluid. Contact resistance may be reduced by increasing the area of contact spots. This is what I said. So, you can apply pressure on the two materials, reduce the roughness of the two surfaces so that there is more contact. Of course, you can select a fluid with a large thermal conductivity, which is what we said is a thermal grease or something like that. Okay. So, we will go to a simple problem which is going to cover these concepts. So, we have a leading manufacturer of household appliances is proposing a self cleaning oven that involves use of a composite window separating the oven cavity from the room air. So, you have one hot cavity and you have room air which is ambient conditions. The composite is said to consist of two high temperature plastics A and B of thickness La, which is twice the thickness Lb. Conductivities are given to you. During the self cleaning operation, the oven wall and the air temperatures are at 400 degrees centigrade, which is inside the oven, and the ambient temperature is 25 degrees centigrade. So, the inside convective and radiative heat transfer coefficient as well as the outside convective heat transfer coefficient are approximately 25. So, the numbers are the same, and find what is the minimum window thickness L, which is sum of La plus Lb, needed to ensure that temperature is 50 degrees centigrade or less on the outer surface. This cannot be exceeded for safety reasons. So, the problem is very simple. Okay, it is a normal thing that you would see in your house. You have an oven where food stuff is getting baked or cooked, and the outside air. So, the oven being at high temperature, the air inside and the walls are at some uniform temperature. The glass that is protecting that is on the door of the oven has two parts, A and B. Thickness of A is twice the thickness of B, the material thermal conductivities are given. You are asked to find the thickness of the wall such that the outside surface temperature, not the ambient is given to you as 25. The outside of the glass, that if you touch, it should not be more than 50 degrees for safety reason. Otherwise, even if you touch the door of the oven, you will burn your hands. So, that is not something which is advisable. So, 50 degrees is the upper limit. So, you are asked to find the minimum window thickness for the same. Okay. So, this is your schematic. So, you have an oven air which is shown here, 400 degrees is the temperature inside. HR and HI, which is the convective coefficients, are both 25 degree 25 watt per meter squared Kelvin. TH air or T wall is also 400 degrees, the oven cavity is shown to you, and that the gap which is there, the door which is there, the window which is there is given expanded view. Ka and Kb are shown. You are asked to find the thicknesses La and Lb such that Ts outside is less than or equal to 50 degrees centigrade. And this problem is very simple, because if you look at what is there on the on the outside, you have T infinity, which is 25. There is convection on the outside. Then you have T surface out, which is the outer wall of the window, which is Tb, T surface out. There is conduction through the wall. So, there is Lb by Kba, and then there is another material of thickness La. So, La by Kaa, and then you have on the inside wall Tsi, whose temperature I do not know, but all I know is the air inside the oven is transferring heat by convection, and the walls are transferring heat to Tsi, the inside of the window wall, by radiation. So, we will write all this together and we will see. So, the circuit diagram is shown. I will draw this separately and then we will go ahead and solve the problem. Okay, we need to make a few assumptions, steady state conditions of course. Conduction through the window is 1D, we have not dealt with 2D conduction, it is primarily 1D from the oven to the ambient air. Contact resistance is negligible. What is that? It is between the two glass window material La and Lb, right. Ka and Kb are two different materials. The contact resistance is negligible. What if it is there? Value should have been given for the contact resistance. So, since nothing is given, it is taken as negligible. Radiation absorption within the window is negligible, so no heat generation. What does this mean? Absorption means if I supply energy to something by radiation. So, I keep something in the sun. Say for example, I keep food stuff in the sun, or I keep a plastic material in the sun. It will eventually take in the heat, absorb the heat, and that will also have to come out. So, we are not talking of that kind of a situation where there is absorption of radiation energy by the window. So, that means whatever is coming in by radiation is also going out by convection. Radiation exchange between the outer surface of the window and surrounding is negligible. We are making this assumption TSO is 50 degrees or lower than 50, T infinity is 25 degrees centigrade, we have H is about 25 watt per meter square Kelvin, natural convection kind of heat transfer mechanism. Ideally speaking, we should have taken radiation on the outside also, but we are neglecting it for simplicity. Each plastic is homogeneous with constant properties, which is perfectly fine. So, we need to draw the thermal circuit diagram. So, let me just go to the set of slides and draw this. So, I have, this is my window, and here I have, this is TSI, this is TSO, this is T infinity. So, there is a conduction resistance in window 1 material A, there is conduction resistance for the material B, there is convection resistance between outside surface and T infinity. 1 over H naught A, this is LB over KBA, LA over KAA. All the areas of heat transfer are the same, which is correct, right? The window of the oven, the sheet, the material, everything will have the same area. So, there is no reason why this is going to be different. Yeah, had I had two materials here, for example, this was material B and this was C, then I would have to say how much is this area, whether this is half of a total area or no. That we are not having in this problem, we are having everything to be the same material. So, we do not have to worry about it. I hope you are able to understand. So, if the split was like this, okay, the window of the oven was made like this, the top half had a different material and the bottom half had a different material. So, what by that I mean, this is material A, this is material B and material C, then I have to find out AC and AB, which is AC plus AB is equal to A, which is what is the area of the window here. Okay. But in this problem we do not have such an issue, so we do not deal with this kind of a thing. So, let us go back now. On the left hand side you have two paths for heat transfer, Q radiation and Q convection. Now, thankfully, why am I saying thankfully? The air and the walls are both at 400 degrees centigrade, TS1 is the same number. So, across the same temperature difference, that is 400 minus TS1, TSI, I am having the heat transfer. Suppose T wall was 500 and T air was 400. Then I will not be able to draw this kind of a circuit diagram. Okay, it is difficult to draw because it is the convection is across a different temperature gradient, radiation is across a different temperature gradient, and therefore, your circuit diagram will become a little complicated. However, here that is not the case. So, I have two resistances in parallel. Let me extend it here. This is your R convection inside, R radiation inside, and both are with T infinity, and that is what is shown to you here. I just drew this again just for clarity. Everything is T infinity. I wrote T infinity, they are writing it as T wall and T A, both of which are again T infinity, which is T infinity on the inside, which is 400. So, let me just change the nomenclature because we have a T infinity here. So, I will just change the nomenclature, T air and this is T wall, both are equal. Now, it is a matter of finding the equivalent resistance. So, I will do the equivalent resistance for this, that is R equivalent inside, 1 over that is 1 over R convection inside plus 1 over R radiation inside. So, that is 1 over 1 by h A plus 1 over h radiation into A. This is convection, this is radiation, both are equal. So, 1 over, this is where we make a mistake. We will write it as 1 by, instead of doing 1 over, there is a tendency to write it as 1 by 20, instead of 1 by 25, we will write it as 25. So, this is 25 into A plus 25 into A, which is 50 into A. Therefore, R equivalent inside is 1 by 50A. 1 by 50. Now, this resistance is going to be in series with the rest of them, which is what we will have. So, this is in series, R equivalent inside is in series with the red ones, and now it is a matter of putting all these together as summation of R total or thermal is R equivalent in plus L A by K A plus L B by K B A plus 1 by H naught A. This is 1 by 50 A plus L A by K A plus L B by K B plus 1 by H naught into 1 over A. This is summation of R total, and just the matter of putting in the numbers. So, we will just go through that. So, that is what is given to you here, whatever I have done. So, you have the largest temperature difference and you put in the Ta minus Tso is equal to the summation of the equivalent resistances, which is equal to Q. I do not know Q, but how do I know Q in a indirect manner? Q actually, these two temperatures are given, which two? So, we know these two temperatures. So, Q is equal to H A into T S O minus T infinity. So, I can find out that. So, Q by A, Q double prime is H into T S O minus T infinity, which is 25 into 50 minus 25, which is 625 watt per meter square. So, this is the heat flux. So, this is a problem where this temperature is no. So, I do not have to go all the way till the end. I can just write Q double prime or Q is equal to H A T, H outside A T S O minus T infinity, which is equal to T wall or T air minus T S O divided by R equivalent in plus L A by K A plus L B by K B B. Why do I do that? I do that because this temperature is known and I have already used this to calculate Q. So, I do not have to worry about this part, I just have to take care of these three resistances, So, if I just go ahead and do that. So, this is a number. So, A's will get cancelled. So, this is going to be T wall minus T S O divided by 1 by 50 plus L A by K A plus L B by K B. You 1 by A is there, K B into area. So, this area will go up, which will be H naught A into T S O minus T infinity. This will get cancelled. 625 there, T wall minus T S O divided by 1 by 50 plus L A by K A plus L B by K B is equal to 625. Now, it is matter of putting in the numbers. These two are known, this is known, this is known, this is known, this is known. There is a relationship between L A is equal to 2 L B. Substitute that here and you will get the required answer. Putting all this here, you will get the required answer. L A is 0.0418 meters and L B therefore is half of that. you will get the total thickness of the window is 62.7 millimeter. Okay. And what is important are these brief comments. The self cleaning oven operation is a transient process. So, steady state conditions may not be reached in the time required. However, steady state operation provides the maximum value of TSO, and hence our design is going to be based on that. Okay. Radiation exchange between the walls in the composite window depends on the inner surface temperature. We said that if the temperatures of the walls were different from the air, the maths would become lot more complicated, and we have basically simplified that exercise. Okay. Okay, that is precisely what I have told. On the outside you have on the inside you have sigma epsilon Twi to the power 4 minus Tsi to the power 4 plus this, and on the outside also you have radiation. So, ideally you would have to take the problem in this part. So, the Tsi minus Tso is what is by conduction through the window. You have convection plus radiation on the inside, convection plus radiation on the outside, but for you to start, you need to start with some approximation. So, you can do an approximation of assuming some temperatures to be equal. So, look, it is a complicated process. You can assume TWO to be equal to T infinity, you can assume a value of emissivity of the surfaces inside and the outside, say 0.9, and then you can solve this for the quantities of interest La and Lb. Okay, that is what is shown here. Okay. Next, we are going to look at 1D steady state conduction with no internal heat generation in a radial coordinate system. So, what is a radial coordinate system and where is it going to be used? I am just going to come to that. So, radial system, it is a very important geometry. So, radial is basically cylindrical or spherical. So, I could have a current carrying wire which is producing heat, and you want this heat to be, you do not want this heat to go out. So, you would apply insulation on the outside. Okay, so, this is the heating element and you have insulation on the outside. So, if I want to draw this like this, this is what it will be. This is insulation, this is the heating element. So, this is a system where heat is flowing out in radial direction. If I other things would be, you have a pipe carrying hot water. Okay. So, from a heater, water is being carried across the room to be supplied to various operations in a hospital, in a pharmaceutical company, in a hostel, whatever it may be. So, I have a pipe which is nothing but a cylinder with a particular wall thickness, and you do not want the water which is coming in at 80 degrees to go to 20 degrees outside. You do not want this, right. So, you will have to have insulation. So, you would have insulations on this which will prevent heat loss. This could be of glass wool insulation or any other type of insulation, but the point is this is a radial heat transfer problem, radial system. So, this is your insulation. So, where heat is going to flow out like this along the radial direction, Q radial. So, this is a cylinder. Of course, we can have sphere also, where I could have a process happening inside a spherical vessel, cryogenic fluid which is there, which is being transported across. So, this will vaporize at 5 degrees centigrade, for example. Outside is 40 degrees centigrade, you do not want heat to flow. So, the sphere is encased in an insulating chamber or insulating material, so that the outside heat flow into this is reduced. So, Q is minimized, so that you have less evaporation of the refrigerant, of the fluid inside. So, multiple applications are there, real life applications where Radial systems come into play. Cylinder, flow through a pipe, the electrical heating of a wire due to resistance inside, prevention of heat transfer in process industries, heat loss in process industries, prevention of, you want to maintain a certain temperature for a particular operation, which means you have to prevent heat loss or prevent outside heat from coming in. So, all these systems could be radial system. Cartesian coordinates, of course, we have seen. In the next module, we will take a look at the radial systems, first with no heat generation and later on with heat generation. So, two parts are there. These two we can do for cylinder as well as sphere. Thank you.